All right, we're live. Welcome, everybody. This morning's few sessions will be mostly on performance. I'm going to start with discussing the work that we did to analyze a lot of the ACL implementations in the kernel. And so I'm going to play the video, and then I'll come back for Q&A.
Hi. This work was this is work that spanned a few months between Nabil Bitar and myself at Bloomberg. The work was iterative in nature. We refined and refactored things over that period with many workloads involved that we had to change and tweak the many permutations of test cases in order to get details, the reduction of variables that when it made sense. Most of the time, this was guided by sifting through experimental data, a whole lot of experimental data, and then saying, okay, yeah, we tested that wrong. Let's do it this way. We hope to share this experience with the community, and hopefully that your journey in analyzing the network stack can build on what we did or on our experiences. We should mention that this work is still ongoing and that we hope to get some feedback that we can factor into our next steps. It's important to mention that while Nabil and I spent a few months on this, two other people contributed to this work, namely Paul Menini and Pedro Tamela, so we'd like to acknowledge them. I'm going to present the work as outlined here, and you can see all the ACL subsystems that we tested listed there. But I want to start again. I want to repeat that caution that we collected a lot of data, terabytes of it. So our big challenge was to find that proverbial needle in the haystack. How do you represent this data using reasonable and fair metrics that can be well understood? We also had limited time to do the work, so we didn't want to test everything under the sun. For example, we didn't test NF tables or U32 and TC. Those were on the list, but they're potentially future work. And despite our pruning of this data, we still have about 100 slides in this presentation. We think that we think are relevant, actually. We'll be doing a lot of abbreviations, but we'll have some back slides so you can go and jump to and get more details. So again, to repeat that we used the trio of IP tables, IP set, and const tracking as the baseline for that guided us to what we needed to test. Okay, so why did we do this? Well, we wanted to take a holistic approach to the whole performance analysis of ACLs. There's a lot of contradictory data sometimes on the internet, on the studies we've seen. Sometimes it's good but incomplete, and sometimes it's not comparable to someone else's results. So we wanted to find out for ourselves. We made no assumptions as to whether IP tables was better than ABPF. So we started with a fresh point of view. Why is this work important? Well, performance has impact on the dollar. The lower your performance, the more machines you're going to need, more CPUs you're going to need, the more electricity you're going to have to pay. Especially, it's not just about throughput. It's also about latency and how many CPU cycles are consumed. I'm going to describe the setup. Basically, I'm generalized over what IP tables does normally, right? So in IP tables, you have a concept of a rule set, which is the rule sets are ordered. If you use the TC lingo, then they're prioritized in a priority order. Each rule set, in our case, constituted an LPM table, which is IP. If you use IP tables, it's the IP set net. So you can insert as many prefixes as you want there. So that's how we grouped IP addresses, grouping source IPs and destination addresses, protocols, and source and destination ports as well. Could be a list of ports, ranges of ports, typically pointing to some application, and of course some basic action like drop or accept, and we collect statistics as well. On a typical setup as well, if you turn on const tracking, then you have a hashing of some form that, you have caching, I'm sorry. So const tracking will act as a hash, as a caching mechanism, and we had similar approach for eBPF that we ended up adding, right? So each of these rules in our case constitute about 50 prefixes. So a single rule set will have 50 by 50, so it's 2,500 rules on overall. And the lookups, basically, if we have caching, it starts with the hash lookup on the cache first, and upon failure, it will iterate linearly. And we structured the testing so that the last rule is where you find your match if it wasn't in the hash table already. Okay, so let me go over the experimental setup. We disabled everything that we were worried was, or as we kept experimenting, we found things that were causing variability in our results. A lot of these things were turned off because of that experience. We sift through the data, we ran multiple sets of data. A few hours later, you look, the data wasn't comparable. And as we kept turning this off, the collection improved a great deal. I'm not going to go over them. These are classical things that a lot of people doing performance analysis will turn off or turn on. But the main point here was to reduce variability. The workloads we tested. Okay, so we tested forwarding. We tested host, both ingress and egress. And for both workloads, we tested again the worst case scenario. If you have linear iteration, you go all the way to the end and you match on the last entry. We tested a baseline where packets just came in, they get forwarded, or they go all the way to this up the stack, all the way to this user space server or client, and then come back out and get routed out. For the ACL pieces, we tested a range from 1 to 3,000 with about 7 counts of rule sets. And again, to repeat, for each of the LPMs, we had 50. So and we always had the 2 source and destination grouping. So 2,500 per rule set. The kernel we used was 513 R6. We iterated over many kernels, but the one I'm presenting the data on here is 513-RC6. And we collected, we ran several sets of the same tests, and we collected perf CPU, and we averaged the last 2. All right, so just a reminder, if you're using IP tables, then, or Netfilter, I'm sorry, if you're doing forwarding workloads, then this is where you place the filters. If you're doing ingress testing workload, then you'll insert the filters here. And if you're using an egress workload, then you insert the filters there. For eBPF, if you're running just XTP, this is where you would insert the filters, and that's only for ingress. For the case of ingress, either forwarding or not, for TC, you will put them in the TC ingress, and on egress if you're testing the output. So I have 30 minutes for this presentation. I already chewed a few minutes. They're giving presentation. So I'm not going to go into a lot of the details. We did a lot of testing on the control plane as well, like how fast can you add rules and how fast can you delete them and under different constraints. And I'm going to summarize to say that eBPF did very well compared to IPset, compared to which did very well compared to IP tables. Your mileage may vary. Sometimes, I mean, the CPU consumption of eBPF, because it's synchronous, was slightly higher than IPset, which is asynchronous and uses Netlink. We're not going to show IP tables at all. We're not going to show rule sets with IP tables, I mean, results for rule sets with IP tables that did not have IPset in them. At some point, it got so bad that we stopped testing, basically, for IP tables without IPset. So I'm going to say that if we tested, let's say, a bunch of rules that had IP sets, the equivalent of the worst case scenario is captured there. We're also not going to show data, latency data on forwarding, because we had some issues with T-Rex version 2.8.2. There's a lot of newer versions since then, but we haven't tried to upgrade and check our results. We did test Flower extensively, but we're not going to show much data on it because it doesn't quite fit the trio of the trio semantics that we're looking for. We can make it work, but it will require a lot more complex control plane. And just to summarize, Flower works very well if you have a fixed mask per table. Once you start mixing masks, trying to play like an LPM table within a single table, then things get very bad. Okay, so our analysis. Did I say we collected a lot of data? And among that data, if you just looked at PPS, I mean, two tests may show the same PPS, but they're not the same, right? So we came up with these two metrics. Take the PPS that was achieved, normalize it over the CPU utilization that was used to achieve that rate. Likewise, take the PPS that was achieved and normalize it over the latency. So these are the two metrics which I'll keep using for showing the results. So PPS per CPU and PPS per latency are the data results that I'm going to show. We had some bias. The bias was that XTP-TC, for example. I mean, the people who love XTP and TC BPF will say, why didn't you just bypass the stack and go all the way to the egress using Mired, for example? We wanted to have an orange to orange comparison, so we let the packets go up to the stack. And actually, as a matter of fact, at some point, the stack was the bottleneck for both of them. And for caching, let it be said that con-tracking does a lot more than what we did. It does stateful connection tracking, and we only used it for the sake of caching. Although the point is that in our testing, we made sure that the caching never overflowed. So probably the effect is not as big as it should be. Okay, so let's start with the testing. This is the hardware we used. It was a motherboard that had a Xeon Gold 6230 CPU at 2.1 gigahertz, so it's not very high on the frequency range. It's got a lot of RAM. We turned off hyper-threading. It only had one NUMA node, which is great for testing. It has an Intel XXV710, which is a dual-ported 2x25, connected directly on the core through PCIe Gen 3 by 16. Our test setup had two exact machines that had the same motherboard on both sides. This is for forwarding. The test on the side of host is slightly different. So T-Rex creates servers and clients. It's very capable of creating both clients and servers and then monitoring both sides. Love T-Rex. It's got a real TCP stack. So we used the TCP profile it has. We didn't want to run too many short flows. So we picked something in the middle. It's not an elephant, neither a mouse kind of flow. It had 300 packets, bidirectional. It was about 150 packets, about 80 bytes on each direction. T-Rex was set up to create up to 60,000 connections per second. We tested this to make sure that we picked the rate to minimize the drops. There were very, very, very few drops with that. So if you looked at the drops and at the connect, you would not be able to deduce what ACL subsystem did well. T-Rex measures PPS, packets per second, connections per second, bits per second, latency and drops for both directions, for both its sending and receiving sides on both ports. It also collects a lot of TCP data. I'm not going to talk about the latency because we didn't use that feature. We compiled two kernels. I should mention that, one with Netfilter and the other one without. It's kernel 513 RC6. This was for all the tests we did. On the system on the test side, which is this system here, we run RSS. So we consumed all the 26 cores. And we created, of course, really nice traffic patterns so that all the 26 CPUs were basically equally exercised. And like I mentioned before, we have those rule sets. We run the 7 ACLs, and of course we collect CPU and parf results here. So if we can always go back and dig in and study those data, and then we may rerun the test. For the eBPF, both for XTP and TC, we created our own tool, which we call P-tables. That's going to be described in another talk. I'm not going to go over it. Please come to that talk. For forwarding, we created a cache. For when we used caching, whether it's contracting or in the case of eBPF, we always set the cache to be about 8 million entries, because we knew during any set of test run we would create about 6 to 7 million flows. So it didn't matter. So we never wanted to deal with cache eviction. All right, let's go over the results. So I'm going to start by going over the what we had, the metric I described earlier, which is PPS over CPU. So PPS normalized over the CPU used to achieve the rate. The base is pretty high, it's above 1.75 here. You can see now that TC over here, I mean eBPF, whether it's XTP or TC, did much better than just IP tables rule sets with no caching. IP tables rule sets with no caching at some point got so bad we stopped testing after 700 rule sets there. Contracting, caching always improved over the status quo. So if you look at contracting, you always get better results with contracting turned on, despite the run a lot of people have against contracting. It actually does improve performance over a period of time. As you can see that, of course, the linear iteration in IP tables in order to create a cache entry to contracting takes its toll at some point. As you can see, at around 3,000 rule sets, things started getting bad. TCBPF as well, when we did not have caching, it was linearly deteriorating. It was pretty good in the beginning for the first two, and on the internet people typically test just with one rule set, so it makes it look very good, but it actually gets bad as you increase the number of rule sets. In the caching scenario, it was pretty good. It deteriorated, but by little, and the same results with XTP. XTP had the similar results because it was, we routed packets, right? So you go through XTP, but you still have to go through the stack. So the results were not much different than TC. All right. This is what I just said, so you can read it afterwards when you get access to the slides. Now we reboot again with Netfilter compiled out of the kernel, and just show our perf results for the previous kernel where we had Netfilter on. You can see the yellow is effect of consumption by Netfilter. Reminder, we had 0 rules at this point. When we're testing eBPF, we do not have any rules in the kernel that using Netfilter. Just hitting the hooks was pretty CPU consuming, as you can see. So you look at TC versus with Netfilter off versus Netfilter on. We did get, at least for the first 3 iterations of the rule sets, 20 to 30% improvement. Once you start hitting 700 rule sets, we're linearly iterating all the way to the end. It's no longer the effect of Netfilter that rises to the top of the food chain in CPU consumption. It's we start seeing logs hitting in. We didn't spend a lot of time investigating, but the QDIS clock was certainly there. When we hit the caching, of course, we are consistently getting 20 to 30%. So the Netfilter, just compiling a Netfilter has some effect. It's not the only cause of performance degradation, but for that many rules rule sets, it's pretty impactful. This is what I just said. You can read it after. I'm going to go into the host workloads now to describe the setup. It's while we did run RSS on the case of forwarding, we only utilize 2 cores. In this case, there was a client server setup running UDP. So the traffic generator sends UDP packets, and they are time stamped. We turned on PTP, so we have very good latency results with this that are very accurate. Over and over, they're very consistent in what we achieved. We have PTP was turned on to ensure that we get high granularity in latency measurements. We sent about 1K sized packets up to the MLF, maximum loss-free rate. And we collected the packets per second, bits per second, and latency from the traffic generator on the system under test. We tested CPU, and we collected CPU and perf just like we did with the forwarding tests. A short reminder of how things look like when you when the packets come into the kernel, into the driver, hit the DMA ring, NAPI starts pulling packets out. Now you're going to hit at some point, I'm abbreviating this, the ACL processing subsystem that we are testing. And it goes all the way up to the stack. If it's a UDP server, the response comes back out. Okay, so if we're testing Ingress, this will be in there. If we're testing Egress, that will be there. So just as a reminder, we did tie the IRQ to one of the CPU cores, and we bound the server or the client, depending on the test, onto the other core. So we're only using 2 cores, right? Okay, so let's see some results. Baseline, still, as expected, would do best. There was no ACL at all. There's no IP tables, no IP set, no TCE BPF or XTP. So again, very similar behavior like before. We see the normalized results of a CPU, deterioration for all of them. XTP again and TCE do better than IP tables and IP set. The caching, this was a bit surprising to us. The contracting did not improve the performance for Ingress host side, whereas it did in the case of forwarding. Caching did improve things, as you can see, for both. It improved a lot for both, TCE and XTP. Again, there's no much difference between XTP and TCE because we're still going up through the stack and routing packets there, right? Now we show latency, and yes, basically similar results, right? This is PPS normalized over the latency achieved. The best result was still with base. IP tables started doing pretty bad, almost the same. If I flip back and forth, you'll probably see it's a very similar layout. So results basically even with, there is differences. I mean, contracting, for example, did much worse, right? Where you can see, if we pick the PPS normalized over CPU, contracting will look much better than if we just looked at latency, right? On the other hand, anything that was cached, in the case of XTP and TC, did fine. It was the same sort of format result. Flower, this is the only time I'm gonna show it. Yes, everything here was fixed. Any of the prefixes were fixed to /24, and then we tested Flower. It was very, very impressive, I would say, as you can see. More impressive than IP tables and IP set, more impressive than TCE BPF or XTP for that matter. Just as good, almost as caching. Well, if you know how Flower operates, it's a hash table, so it will, this is probably expected. I'm not going to talk more about it. This is a summary which you can read after. And now let's go and turn off boot up the kernel which has no Netfilter on. At this point, again, we see similar results like we saw in forwarding for the Ingress case. The first two, actually, I'm sorry, it's slightly, it's only for the first 2 iterations that we see an improvement. In the case of forwarding, we saw the first 3. But for those 2, 20 to 30%. For the hashing, everything there was an improvement in everything. There's some jitter here and there, but overall, the results were pretty good for the case of Netfilter turned off, right? And that's a summary which you can read after. Now, for the Egress side, again, we just a reminder that the ACLs would run here. Same setup as the Ingress. We had the the IRQ for the port that was being used on one, essentially on one of the cores, and then the CPU, the other cores bound to the application. Right. So let's go over the results with Egress here. Again, it's sort of similar kind of envelope of results. You could say that TC eBPF, you don't have Egress on TC. That's why XTP is missing here. Did better if you compare those two, and if you compare the caching, yes, TC eBPF did better. Again, there was some sort of similar behavior here. We did not see contracting improving over the status quo of just Egress host. There's other reasons that I can go over in details afterwards, maybe if we go on a private conversation. Mostly is how the we are basically CPU bound on the on the system calls more than it is on the software queue. So overall, yes, TCE BPF did better. That's the summary of this, I guess. And that caching for the case of IP tables didn't improve, but it did improve for TCE. Turn off Netfilter, and I'm sorry. Sorry, this is the latency. The PPS normalized over latency is also very similar in this case. There was not much variation if you look at the frame of the test of the results, right? So same results, basically nothing changed from what I said earlier. And here's the summary that you can read afterwards. Now let's turn off Netfilter altogether and just test TCE on the egress. And yes, there is an improvement. Again, just like the host side on Egress, only the first two improved. And the other parts of this graph had other impacts on them. And for the caching, those, like before, the caching did improve 20 to 30%. Now, if you're to look at this, what would have happened if I just did a redirect, that number would have gone up much higher, right? Maybe another 20% improvement. So summary, which you can read after. The conclusion, yes, eBPF does better performance than the trio of IP tables, IP set, and contracting, both from a data path perspective as well as the control. Caching helps always. The only gotcha we saw was with contracting and host level workloads. And that compiling out Netfilter does improve eBPF performance, ranging up to 20 to 30% depending on the workload. We'd like to acknowledge both Paul Menini and Pedro Tamela for all the help and effort and contributions to the discussions on this. And with that, I'm going to leave it open to Q&A. And I think I made my 30 minutes. I hope I didn't rush too many details, but we're going to be available after the Q&A as well at the lounge, talking to discuss any issues or concerns, or if you want to get a little bit more details. We have a lot of other slides, like I said, in the back that you can revisit that discuss a lot of the details. But I would say let's go to the Q&A at this point. Thank you.
Hey, it helps to be admin. I just wanted that applause to go on for a bit. Okay, so, all right. So we'll start with the first question. Anybody that wants to go on stage, please just get started. Raise your hand. I'm going to post a question by Jesse as to whether the RAM channels are what the bandwidth and speed was. So I just SSH'd. I'll post my answer of what I'm seeing. I don't think I can share my screen while I'm posting your question. Okay. Oh, you know what? God damn it! Let's just do it. I'm just gonna. Well, we don't have time, but we can talk afterwards, right? Okay. All right, Jesse, come on.
Sure. Yeah, I was. DMI decode shows a nice summary of at least all the information that you need there to figure out that answer to my question.
Okay, so I have something here. Let me just cut and paste it and see if that's what would.
Or you can throw it. That'd be fine.
Yeah, I'll throw it here. We'd be very grateful if you can figure out something that's wrong here that we'll go back and redo retesting if needed.
Yeah, I doubt. Yeah. I don't think you did look at the numbers that you showed. They were right where I would have expected them to be from my setups too. So I think that everything was probably fine. It just good to know.
Right. Okay. Does that make sense to you? I just posted it on the chat there.
Yeah, and then you need to figure out how many of them you had. Yep. But anyway,
it's outputting a lot of data. I can paste
it. It is. Yeah, it's a ton. Yeah, we'll talk about it later. Okay.
Okay. All right. Thanks. Okay, bye. All right, next one. Next question was from Tom. Tom asked a question as to what kind of cache hit ratio we see. So we have some data, which I'll be, if I remove it from the state from here, I can actually, well, I can share my screen and show the data. What we found, because we're trying to do a comparative analysis across multiple, multiple implementations, IP tables, IP set. What I would say is it was surprisingly unimpressive, the differences. I mean, they were not very big differences. I can share this data afterwards. We did collect cache hits and cache misses. So we have that data. It was not very impressive. Mostly because we're trying to look for differences, right? So if, I mean, the numbers I have, for example, on, what was it? Yeah, I could probably share this screen. Let me just bring you up to speed maybe afterwards. But the numbers were not very impressive. You were seeing, let's say, 0.004% cache miss was about average for all of them. Surprisingly, Netfilter as well, sorry, IP tables as well as contracting had a lot less cache misses than TC did or XTP did. That was a bit surprising for us. But it was not that different. It was like 0.001 differences. So maybe we can have that talk afterwards. If you want to come on do you want to raise your hand if you want to speak to that? Yeah, okay. Go ahead, Tom.
So my question was more in line the workloads you're measuring. So in a realistic workload production environment, do you think you see the same cache hit ratio in this test?
Yeah, so even in the case of very low traffic, it seemed very, no, I would say no, because as the higher the load, other effects starting showing up, like a lot of locks pop their heads up. So I don't think under normal circumstances where you have low traffic, for example. But given our tests were sort of in the 50.
I guess my question is more, are the tests you're running, are these emulating real world conditions, or were they completely synthetic?
The host ones were certainly, absolutely testing let's say a market data kind of performance tests. The forwarding ones were mostly trying to test how fast we can exercise, how much we can beat up, let's say, IP tables or TC, and see how well it handles that load.
Okay, thank you.
All right. Yeah. All right. Next person on question here was from Shrijit. I'm going to show it on the stage. Is PPS getting better, but PPS latency getting worse? Is it saying the CPU is blocking the data? So that's a very good question. This is one of those things that, for example, when we were testing the host, and if you want to come on stage, just raise your hand, Shrijit. When we were testing host level traffic, not the forwarding. The forwarding is a lot of the activity was on soft IRQs, but once you start going to host level, where you're starting to hit system calls, you're crossing kernel to data path. The user application is also consuming CPU. Depending on how you schedule, you may get the same throughput for 2 runs, but if you put everything on a single CPU, you may get the same throughput, but the latency was a lot worse when you have only one CPU. If you just looked at PPS, you wouldn't know the difference. They look the same. Hey, I got the same PPS. So I am not sure, quite clear as to why. So one thing I would say definitely is probably scheduling has a big effect on this, right? Especially for host kind of workloads. I don't know if I answered your question. Somebody raised their hand, and it is Shrijit. Okay, there you go, Shrijit.
You did. I think that was the question, right? Because that's a very suspicious divergence. If your PPS per CPU is getting better, as in you're using less CPU to get to the same PPS, but your latency is going up, it basically means somewhere. And the next question was really, what's the methodology for how you're measuring CPU? Because if CPU is user CPU, then the block would actually do exactly what you're seeing. If it is total system CPU, then no, because the CPU is obviously, hopefully, doing something else. But that was a vicious break, right? Some of your data point had divergence between the two.
Yes, and we didn't want to sort of hump on just one, but definitely host level activity requires a lot more tweaking and tuning, because you're hitting all the three levels. Like you're hitting soft IRQ, you can see the user CPU numbers going up, the system calls, and how you tweak it. We ended up sort of splitting them into two CPUs, like I said in the presentation, just to get to reduce the latency more than it is to PPS. PPS was okay with one CPU, given the traffic rates we were sending.
Makes sense.
Right.
Makes sense.
Yeah. All right.
I'm curious to hear the answer to the next question.
So, sorry. What is it? Oh, that's
I'll
not
jump
you.
out.
Okay.
It's Stoker's question.
Okay. All right. So, all right. Okay. Stoker next. Let me just put that. Yes. So, actually, it's a really good question. So we've been tossing this around, and so the one problem we have with Netfilter is that it's unconditionally being exercised. That code path is, and raise your hands, talk if you want to come on stage. It's unconditionally, you're hitting these hooks and you have no choice. You have to go in there and out. If you look at the packet flow, for every packet that goes out or in or into the stack or forwarded, you will hit this multiple times. All the hooks. There's new hooks now on the Egress side as well, and there's talk of adding more on the Egress. So Netfilter is expensive from that perspective. So I had no rules, and you saw what happened. One approach is perhaps making them static. So if I have no rules and I'm not trying to use Netfilter, I shouldn't be hitting that overhead. And for some reason, we had a really hard time, by the way, loading Netfilter as a module with the newer kernels. So we had to really had to build two kernels separate. I don't know if that answers your question. Oh, okay. Okay, Florian is here. Go ahead, Florian.
So basically, you contradicted yourself with what you said, because the perf data you showed has both the IP tables interpreter and the NFHOOK slow function, and neither should be called if you truly have Netfilter disabled. Because the way.
So which slide are you talking about?
One of the slides that mentioned the overhead of having Netfilter compiled in. Because if it's truly 20 to 30%, then we do have a big problem. And I don't think it's that much. It should barely be noticeable, because this is protected by a static key and it's in an inline function, and it should never call the NFHOOK traverser at all.
Okay, let's have a conversation after this, but this is the data we have, and it's very easy to reproduce. Okay. I think you're probably speaking about the slide where I showed, just before I showed the Netfilter versus no Netfilter on. That was just showing the previous kernel that was running with Netfilter on. I think that's the perf data you probably refer. Right. It just showed that, okay, now we're going to talk about no Netfilter on. This is what we saw earlier, and now we're going to turn it off and see what happens. But the perf does not at all show Netfilter when we turn it off. Right? You don't see the hooks being hit. Mostly because we didn't compile them in at all. But there's probably a way to optimize this. I'd really like to pick your brains on this, see if we can improve things. Right?
20% is a disaster. If that's true, it's a disaster.
Yes. So I tried to ping you guys at that time. If you remember, there was back and forth, but didn't. That was when I was running these tests. So we should absolutely talk after this, right? All right. I'm gonna hand the mic to Talk now. All right, Talk. You go ahead.
Yeah, I think you guys mostly covered it, but I think it would be bad if we ended up in a situation where everyone starts compiling out Netfilter from the kernel to improve the eBPF performance. So like maybe posting the reproducer, taking this to the list and getting this fixed. And yeah, my immediate thought was what you mentioned as well, just hiding it behind a static brand.
Yeah, so interestingly, I think I don't remember seeing this. Maybe I'm running all the kernels, but Florian said it's essentially the static headers are already there, right?
Yeah.
There's
so,
yeah.
But I'm fine with just take if you can post a reproducer or something, and we can look into that. That would be awesome.
Yeah. I'll be more than happy to share this after. All right. Next question is from Shmulik. I'm going to show it. Okay, so this is for no idea, but I'm glad Florian is here. Maybe we can have this discussion after. I'm afraid we don't have much time. As you can see, I rushed a lot through. We have a lot of data, but I really had to rush through representation. Maybe we should check into improving the 30 minutes next time. But I don't know. I didn't look closely into why. But one of the angles, I think, just as I responded to Srijit, it's a very different ball game when you're doing host level performance analysis. You on the ingress, you're being, the socket queue gets filled up at some point. The application may be scheduled in or out. You're mostly CPU bound. That's what we had seen. Right, so maybe that's one of the problems we saw. But this requires further analysis. Our challenge was we want to do performance analysis, not essentially dig too deep. There's just too much stuff to do, right? We did a lot of experiments, like I said in the presentation. All right, next, do you want to come on stage, or that satisfies the answer? Okay, I'm gonna. All right. Great, thanks for the thumbs up. Okay, next question. Oh, somebody says I should show the shirt. Yeah, okay, there. Unfortunately, we didn't ship t-shirts now because unless somebody wants one, they can ask and then they'll have to pay for shipping. What other question do we have? Okay. Do you intend to open source? So here. Yes, so we ended up building a lot of infrastructure around this. So, we're running T-Rex, we could run iPerf, and yeah, it's mostly, we'll probably open source. We're not 100% sure on this. But if you want to talk to us privately, we can have a conversation as to how we, our problem is supporting it. It's a bit of a challenge because it's a very big infrastructure. It integrates with many traffic generators from all the way from T-Rex. So you can reproduce our test with T-Rex if you're just doing the forwarding tests. We can share our methodology in details after. And any more questions? All right, so okay, so there's some comment from David Arhan, but I guess no question there. He says, oops, oh, well, it was a +1. I got the wrong one. I see a bit of overhead on modules. Sorry, that's the wrong. That was Jesse saying he sees a bit of overhead when modules are loaded with no rules. So I'm not the only one seeing this. Yeah, that looks like it. If there's no more questions, we can wrap this up. Thank you. Woo, yes, more. Okay, and for that, and we're going to wrap this up. Thank you, everybody.